All right, today's lesson is about the particle model. We're going to jump into kind of the more modern take on static electricity. But before we get started, I want to encourage you guys, make sure you guys are putting your text documents up, right? Your short answer and multiple choice text document and your long answer and diagrams and list document. Write down questions, pause the video, make questions as you go, because then you can watch the video once and probably be done. However, when I was in university, I would probably watch the video lectures or go over the lectures a couple times to get all the questions. Keep in mind, you can also speed these videos up if you're just looking to do questions. You can watch it once, then watch it at 2 times speed, pause it, and put the questions down. But I want you guys taking those questions down because we're going to be using that at the end of this lecture. It's going to be attached to your assignment for today. Okay, the particle model. We know like charges repel like charges and opposite charges attract. But what about neutral objects? Over here, this all makes sense. If you have magnets or if you have an object, they attract or repel. But we know that neutral objects can be attracted to charged objects. You guys have probably seen this before. If you rub, a balloon or something on your hair, you can stick it to a wall. Is the wall supercharged to one way or the other? Probably not. So why can neutral objects be attracted to charged objects? The previous models, the old models, this kind of confounded those models. It didn't quite make sense. The particle model attributes electrical charge to electrons and protons. And if you remember, I hope you do, electrons are negative, protons are positive. We haven't been out of school that long, I hope. Uh, and everything has electrons and protons in it. So there are negative and positively charged things in everything. If something has a charge, it means it's got more electrons than protons or less electrons than protons. But those electrons and protons in a charged object can interact with the electrons and protons in a neutral object, just like they could in a differently charged object. So how does the particle model explain what's happening when a negative object is attracting a neutral object? Um, I'm going to draw the balloon example for you guys because it's easier than trying to explain it. So let's see here. Okay, so let me pull out my tablet and we'll get started. If you guys want, you can rub a balloon on your head and follow along, I suppose, but it's not totally necessary. All right, so if we've got a balloon here, let's see how good my art is. Ooh, it's not good today. No different than usual, I suppose. So here's our balloon, and let's say we rubbed it on, not my head because I have no hair, but on somebody's head, and that balloon actually becomes negatively charged. Okay, it's got a lot of electrons attached to it now. So there's all our electrons. And we're going to stick it onto this wall. And this wall has a bunch of protons and electrons and an even number of all of them, right? So we've got an even spread of protons and electrons there. But when we move that balloon towards that wall, something weird is going to happen. So all of our negative electrons are going to be over here. And what's going to happen to the electrons and protons in that wall is negative charges are going to repel each other. So our electrons are going to kind of shift over to the right side. And obviously, it's not like the entire wall has electrons on the right side. It's every particle in that wall, the electrons are shifting away. Okay. And all the protons are going to be attracted over to this side. So because you bring a heavily charged object near a neutral object, it actually manipulates the subatomic particles in that neutral object and creates an attraction between the two, just like it would with a charged object. Okay, so the balloon phenomena, or you guys have probably played with that before, um, is explainable this way. If something has 8 quinzillion electrons, I made up that number by the way, just a lot of electrons, it's going to exhibit a force on the electrons and protons in a neutral object. Now, obviously, this should mean the balloon example works, but I was thinking, what about like a potato or something? How come you don't have, if you have something like supercharged to really positive or really negative, how come like the potato doesn't just like slide across the table to it? And I don't know, maybe you guys can figure that out. My best guess is that a charge that is that strong will get dispersed really quickly, like into the air or into whatever it's touching, because a potato is significantly heavier than a balloon. So I think, and this is just kind of an educated guess, that if you have a really significant charge, a charge significant enough to move something heavy, it'll get dispersed too quickly. But, thought-provoking question, the potato question. We'll see. Maybe someone will come up with an answer. Okay, so our neutrally charged objects, according to the particle model, have an equal number of protons and electrons. A positively charged object has fewer electrons than protons, which means that you have less negative than you do positive, so your net charge is positive. And our negatively charged objects have more electrons than protons. You have more negative than you do positive, net charge becomes negative. Here's an important thought-provoking question for everybody. The word macroscopic just means big, so like not microscopic. So is any macroscopic object actually neutral? And I was thinking about this while I was making this lecture, and I realized that the answer is probably no. So then I looked it up, and my research kind of confirmed that. Macroscopic things generally have a bit of a charge. They have a little bit more electrons, or a little bit more, or a little bit fewer electrons than protons, because when things rub against each other or touch each other, inevitably there might be some transfer of electrons. And that's going to create a small charge on most things. So generally things won't be actually neutral, but things are very close to neutral a lot of the time. I think a good example is styrofoam plates. I think when you pull them out of the package that they come in, they generally have a bit of a negative charge on them. So let's think back to Bohr models and what defines an element. Hopefully you remember. It's protons, by the way. The number of protons that an atom has is what defines what element it is. So what subatomic particle do you think is being transferred between objects when they're getting charged? And if you think it's protons, I want you to keep that thought in your head for a second. Well, no, we'll talk about it now. If you think it's protons, that would mean that if you took something well, we'll use the classic example, rabbit fur in a glass rod. If you took the rabbit fur and rubbed it onto that glass rod, and it transferred enough protons to one of those objects, eventually that object would become gold because the protons would change the atoms in there to become Au, or to become gold atoms. So we know because that doesn't happen, it's not a transfer of protons, it has to be a transfer of electrons. So let's draw an example. We'll get rid of this old drawing I have. Let's see here. My beautiful art. Okay. So the rabbit fur and glass rod idea is that you take you take a glass rod like this. You take a piece of rabbit fur. I don't know how to draw rabbit fur. Maybe like that. That's a rabbit fur. And you rub this rabbit fur back and forth along this glass rod, and there's a transfer of electrons. So if we zoom in there, let's say this is the surface of our glass rod, right? And we have our nucleus and we have our atoms here, right? This is like our little Bohr diagrams. I'm not going to draw all the electrons, okay? I'm just going to draw a couple for example's sake. So we've got a bunch of atoms, and we're rubbing our rabbit fur. This is our rabbit fur. back and forth across this rod, then what's going to happen is the electrons on this valence here, or like on the outer ring, the valence electrons are going to actually jump across and get added to the rabbit fur. So if this glass rod is losing electrons, then the glass rod becomes positive, right? It'll change our charge to positive. And the rabbit fur, its charge, because it's gaining electrons, is going to actually become negative. Where are we here? So the particle model, it's electrons. It's always electrons. Electrons are always the ones being moved around. If you moved around if the protons were moving around, stuff would get weird. So electrons are transferred between objects, creating imbalances of electrons and protons in each object, resulting in the charges of each object changing. So back to our original questions. Why and how does the styrofoam plate float? Why and how does the can roll towards the tube? I want you guys to just kind of mull these over, consider these. We're going to have a bit of an assignment on this later. But for today, your assignment, this is the end of the lecture, but your assignment is to go through the questions that you have written down, which I hope you did. I know you did, of course. I want you to take those questions and I want you to post your best one as a reply to this assessment or to this like lesson on EDSB. Okay. And the rule is you can't post the same question or a similar question to somebody else who's already posted one. So I hope you woke up early and watched this. Okay, everybody, cheers.